Okay, so we're starting our new chapter today. And in the new chapter, we will mostly look at applications of integration. So contrast that with the last chapter that we just covered, which was techniques of integration, right? Every section we covered was a new technique of integration. So here we assume you now know enough techniques of integration, you know how to integrate, and we're going to look at applications of integration. And the first section is about area between two curves. So in the first 5 or 10 minutes, we're going to derive some formulas, and then we're going to do some applications with those. We're going to do some examples. In the first example, as you can see, we have two functions, f of x on the top and g of x on the bottom. Now, you have already learned in Calc 1 that if you have just a function, such as, let's say, something like this, if you just have a function, and if you're going from the point A to the point B, how do you find this area? If you know the function is f of x. Yes, Joshua?
Integrate and then take and then use the
Antiderivative. Right. Basically, you find the integral, right? You integrate the function over the interval. So we had learned in Calc 1 that area under a curve can be found by, especially for a positive function in that case, it was by integrating the function over the interval from a to b. And so the only difference then in this section is we have two functions that we're dealing with, not just one function. In the first scenario, we have a function on the top and another function on the bottom. And I'm going to be very careful as I derive the formula. Even though it's a pretty simple formula, the first thing I'm doing is I'm selecting a representative rectangle from the given region. And what could I call the thickness of this rectangle? Let's think about that for a moment. You're going from a point on the x-axis to a point x plus another incremental distance in x, which we call usually delta x, right? So the thickness of this rectangle is delta x, because you're going over, from a point along the x-axis to another point along the x-axis, so that distance we call delta x. Now, what would be the height of this rectangle? If the top function is f of x and the bottom function is g of x, what do you think is the height of this rectangle? In terms of f and g, what would be the height? So you have a rectangle here. So you happen to know that this point right here is the point y equals to 2. This point right here is y equals to 10. How do you find the height of that rectangle in that instance? You subtract the higher distance minus the lower distance. So in this case, what you have is the top function is given by f of x, and the bottom function is given by g of x. So in general, what will be the height of that rectangle? Exactly, f of x minus g of x. So that's the height of our rectangle. The thickness is delta x. Now, what is the area of this one single rectangle? What is the area of this rectangle? So if the base is delta x and the height is f of x times g of x, the area of that one rectangle, which I'm going to represent by delta A, area of this one rectangle, is equal to what? Exactly, length times width, right? So the height of this rectangle is f of x minus g of x, and the width is delta x. So for this one rectangle, it's basically length times width, which is f minus g times delta x. Now, what if you had n of those rectangles? In that case, you would sum them up, right? You would say summation of f of x minus g of x times delta x. And let's say as I goes from 1 to n, so I'm going to give subscripts to this, x sub I, and delta x sub I. But if we assume all the delta x's are the same thickness, so basically what I have right now is I have n rectangles next to each other covering this area. And again, you can use the right endpoint, the left endpoint, etc. Now, in order to get a perfect coverage, what is the ideal thing? We don't really want n rectangles, but how many rectangles do we really want to have a perfect coverage under this, between these two curves? we want infinitely many rectangles, right? Because if you have like just 2 or 3 rectangles, you're going to have a lot of overflows or underflows. In the limiting case, as n goes to infinity, so if you can do this, let n go towards infinity, then you're going to have a perfect coverage of the area under this curve. But to clean my figure, I'm just going to show one represent a rectangle there. This would be the exact area under the curve. So this quantity would be the same as the area between f of x and g of x over the interval from a to b. Luckily, in Calc 1, we came up with a much simpler expression for this limit. The limit of a sum had a shortcut notation. Does anybody remember that? Actually, we did a lot of examples which were using Riemann sums, etc. But how do we simplify? How do we simplify this sum, the limit of a sum? Does anybody remember that? How do we simplify the limit of a sum? What calculus notation replaced that when we were finding area under a curve? When we're finding sum of infinitely many rectangles, what is that limit of a sum? Which mathematical expression replaced that? The integral symbol, right? The integral symbol, because the integral is the limit of a sum, basically. So that limit and sum is replaced by the integral, and then f minus g still stays as f of x minus g of x. And your delta x, what did that become in your integral notation? Instead of delta x, what do we have? What do we usually write in the integral notation? We write dx, right? And the limits are from a to b. So again, this whole integral idea came from first adding up n rectangles and then taking a limit as n goes to infinity. That gives us the exact area. And the fundamental theorem of calculus told us you don't have to do this long process, limit of a sum. Just find the antiderivative or find the integral of this quantity and plug in the limits, and you will find the area of that region. Now, sometimes they will give you a region a little bit differently. So by the way, what I just wrote can be written in words as to find the area between two functions. You can say integral of the upper function minus the lower function with respect to x. Okay, sometimes they're going to give us the region a little bit differently. We might have a region such as this one, where there is no clear top function and there is no clear bottom function. What could we do in that case? Let's think about it for a minute. First, let me show you what would happen if I pick the same kind of rectangle for this figure. If you like, please do not write what I'm about to do right now. What's going on here? Okay, so if I pick the same kind of rectangle, you see over here my neighbors would be this red curve on the top and the bottom. But over here, I'll have different functions, right? I'll have different neighbors on the top and the bottom. So the same kind of rectangle is not working. You don't have a clear definition of a top function and a bottom function. What would be a better choice here? What would be a better choice? How should we choose our rectangles so throughout the region we have the same neighbor on one side of the rectangle and the same neighbor on the other side of the rectangle? How would you pick your rectangles? Picking them up and down is not working very well. Does everybody see why not? Because you are here. Your neighbors are the red curve, right? You are here, your neighbor is a line and the blue curve. You are here, now it's completely different neighbors on top and the bottom. This is going to be, you cannot define it as a single representative rectangle. So what can we do instead? How about horizontal rectangles? Let's try. Pick a horizontal rectangle. Do we have the same neighbors throughout the entire region? Yes, no matter where you are in the region, if you're using a horizontal rectangle, on the right-hand side you have the f of y function, on the left-hand side you have the g of y function, so this works. This representative rectangle will cover the entire region uniformly, meaning with the same neighbors. Okay, so based on what we just learned from above, again, first you're going to have n rectangles, then you're going to take a limit as n goes to infinity. But just note for the first rectangle that we have here, what is this width here? Can I use delta x again there or something else? Delta y. Why delta y? Because now you're going along the y-axis, right? From a point in y to, you're incrementing it a little bit extra along the y direction, right? So that's why it has to be delta y this time. And how about the length of this rectangle? What is this distance going to be? Exactly. This time it's going to be right minus left, just like it was top minus bottom previously. Now it's going to be f of y minus g of y. So the integral, or the area between two curves, is going to be equal to the integral of the right function, in this case f of y, minus g of y, the left function, dx or dy I should put now. dy. And how about the limits of integration? It's going to go from c to d. Now, a few things that we should pay attention here. In every section that we cover in this chapter, I'm going to tell you, start by picking a representative rectangle. That rectangle will tell you whether you're going to work with the x's or the y's in the given problem. Okay, whether we're doing volume, arc length, or area, like in this case. Okay, you pick your rectangle first. Make sure that your rectangle covers the entire region uniformly. Same neighbors on the top and the bottom, or the right or left. Okay, once you decide on your rectangle, decide on the thickness of the rectangle. In this case, it's delta y, right? Once you do delta y, put the dy in your integrand, because you know that means everything must be written in terms of y. And how about the limits of integration? If you have a dy in here, where should your limits of integration come from? From the y-axis. If you have a dx, then the limits of integration should come from the x-axis. Okay, so first thing to decide is pick your representative rectangle, decide whether it's going to be delta x or delta y. Based on that, you can set up the entire function, the entire problem, whether it's top minus bottom or as right minus left. So once again, if we write it in words, this is what we end up with over here. So in this case, it was right minus left times dy. And we're going to do many examples about these two formulas that we just looked at. Has everybody got that? Okay, so the first example. Okay. Let's find the area between y equals 12 minus x squared and y equals x squared minus 6. Okay. For all of these questions, it would be a good idea to first do a graph to see where the function intersects, to see which one is on the top, which one is on the bottom, or similarly right and left. So it would help to do that. Some of them, you may actually need a graphing calculators. This one we really don't need a calculator for. It's a pretty straightforward function. For example, x squared minus 6. What kind of a graph would that be? X squared minus 6. So let's go in units of 2, 4, 6, negative. So x squared minus 6 is a parabola that opens upwards, right? Because x squared is positive. And minus 6 means it's been shifted 6 units down. So here is, roughly speaking, our function there. And how about 12 minus x squared? Again, going in units of 2, say this is my 12. So what will that function look like? Does it open up or down? 12 minus x squared. The negative x squared is telling you it's a parabola opening downwards, right? And plus 12 is telling you it's been shifted 12 units upwards. So roughly speaking, this is what the graph is going to look like. Again, this is not up to scale, and My intersection points may not necessarily be showing correctly here. If you graph it on the calculator, of course, you're going to get the general idea. But I just want a very rough picture here because I want to be able to see which one is on the top, which one is on the bottom. But I still have to solve some equations to see exactly where they actually intersect. What kind of a rectangle would you select here to find the area? What kind of a representative rectangle? Something like this or something sideways? A vertical or horizontal? A vertical one throughout the entire region, it will cover uniformly, right? The thickness is delta x. So this is one of the first type of problem where we're going to go top minus bottom. So the area will be the integral, the limits to be determined right now. But so which one am I putting first? minus x squared, that's the top function, right? Minus the bottom function, which is x squared minus 6 dx. Okay. And how about the limits of integration? For every one of these questions, even if you do the graph on the graphing calculator, I'm going to ask you to show me your work as to where the functions intersect. What could we do to find it analytically without having to refer to a graphing calculator? How do we find where two functions intersect? Oh, right. For intersection points, what do we do? Exactly. Set them equal to each other. So to see where the two functions are the same. In this case, the functions we're looking at are 12 minus x squared equals to x squared minus 6. I'm going to keep everything on the right-hand side. So here I have 2x squared by adding x squared to both sides. And then subtract a 12. So what are the intersection points of these two curves? Exactly. So this can be factored as x minus 3 times x plus 3. So 3 and negative 3 are the intersection points. So that means we're going to integrate this function from negative 3 to positive 3. Okay, so let's just go ahead and integrate. And you're going to find in this section that the integrals themselves are not problematic. Usually the most work will be done towards setting up the problem. Once you set it up, integrals are going to be pretty straightforward. So once again, I'm integrating from negative 3 to 3 of 12 minus x squared plus 6. That gives me negative 2x squared plus 18. Now, could I do a little shortcut here? Instead of integrating from negative 3 to 3, could I integrate from 0 to 3 and then double it? Perhaps my picture is not so perfect. It's not showing perfect symmetry there. But if you were to graph it on the calculator, you're going to see that there's a perfect symmetry across the y-axis. And how can I know that without even looking at the graphing calculator? I look the integrand over here, negative 2x squared plus 18. If you replace x with negative x and get the same function back, that means you're integrating something that is symmetrical with respect to the y-axis. That means you can use this little trick. Instead of going from negative 3 to 3, what am I going to do then? I'm going to integrate from 0 to 3 and multiply the answer by 2. It just helps a little bit when you are plugging the numbers in. So integrating the function. And we're going to go from 0 to 3. Okay, I'm going to give you a moment to finish this and let me know what you're getting. And we'll get 72 for the answer. Again, even if you did not do that little trick that I did with 2 times integral 0 to 3, even if you went from -3 to 3, you should, of course, obtain the same final answer. Correct. Sure, that would be fine. Okay, another example. Okay, any questions about the first one before we try another example? All right. The question is, find the area bounded by the functions f of x equals 1 over 1 plus x squared, and let's say h of x, which equals 1 over 2 times x squared. Find the area bounded between these two curves. Okay, our first example had to do with a parabola, right? And with a parabola, we could graph it without a calculator. This one, it's okay to make some use of a calculator if you have to. Of course, h of x equals 1/2 x squared. That one, we know what that looks like, right? That one will be a parabola, 1/2 x squared, that opens upwards. It's not as steep as a regular parabola because the 1/2 factor makes it a little bit less steep, right? But how about that one, 1 over 1 plus x squared? Not everyone may remember what that looks like. So for a question like this, I think it would be all right to look at the graphing calculator. So let's do that. Let's go to our graphing calculators. And let's go ahead and graph both of these on the same coordinate system. So I'm going to go to y equals, and my first one was 1/2 x squared. So let me just put 0.5 times x squared. And the other one was 1 over 1 plus x squared, right? So I'm going to do 1 divided by, in parentheses, 1 plus x squared. Now, let me just first graph it with zoom standard. That goes from -10 to 10 on both the x and the y axis. So I'm going to go to zoom standard, which is zoom 6. Okay, this is 1/2 x squared, and the next one is your 1 over 1 plus x squared. Now, I don't think this graph is acceptable because the important part of the graph is happening around the origin. We're wasting so much space. We should go back and change our range and make this graph a little bit better to visualize. So let's go back to window. X minimum, I think I'm going to cut that down, let's say from -4 to 4, because I noticed that we're wasting a lot of space both along the x and the y axis. And for the y, it was so close to the origin, that other graph, perhaps I'm going to go from -1 to 2. Cut it down quite a bit, the space that was being wasted. Now let's look at the graph again. Again, this is the 1/2 x squared. And I think this is much better graph of what is happening around that region. The other one is 1 over 1 plus x squared, which looks like a bell-shaped curve, right? So which region do you think they want us to calculate here? The region, that middle part, right, intercepted by those two functions. So we need to find that region, and let's go ahead and do so. Okay, let's see. I think I'm going to go ahead and copy that graph to my page. Okay, unfortunately, it's not working very well today. That's okay. I can just put it by hand. Okay. Okay. So basically, the other graph was something like this, a bell-shaped curve, roughly like that. Okay. So the region we're trying to find is the middle region. What kind of a rectangle would you like to select from that region, vertical or horizontal? Once again, vertical, right? Easily, if we pick a vertical rectangle throughout the whole region, we have a clear-cut upper function and clear-cut lower neighbors, so this will work. The thickness, once again, is delta x, right? And we just don't know at the moment where these two functions intersect. We're going to determine that in just a little bit. But let's just do the setup right now. So area equals the integral of, once again, which one is the upper function? No, that's the lower function, right? That opens upwards. We want to do top minus bottom, right? Right. So the one that looks like the bell shape here, which is 1 over quantity 1 plus x squared minus the quadratic, which is 1/2 times x squared dx. So we have top minus bottom. And now we just need to find the limits of integration. Once again, how can I find the limits of integration in this case? Just like last time, exactly, William. Set them equal. Let's do that. So set 1/2 x squared equal to 1 over 1 plus x squared. How could I solve this equation? Good idea. Multiply both sides by 2. So you have x squared is equal to 2 times 1 over 1 plus x squared, which is going to be the following. Okay. So what we're doing right now is to find the points of intersection. So we set the two functions equal. And what would you do next to solve this equation for x? Yes. Cross multiply. Let's get rid of all the denominators that way. So consider this as a 1 on the bottom now. So you have x squared times quantity 1 plus x squared is equal to 2 times 1 or 2. And I'm going to keep distributing this. So x squared plus x to the 4th. And bring the minus 2 to this side. And finally, I'd like to rewrite this in such a way that the highest degree term comes first, then the next degree term, etc. So x to the 4th plus x squared minus 2 equals to 0. Okay. So let's see if we can factor this out. X to the 4 as x squared and x squared. And negative 2 as plus 2 minus 1. Because 2x squared minus x squared will give us the middle term of 1x squared. And 2 times negative 1 is negative 2. Okay. Take a moment, please. I want to hear from you. What solutions do you find to this equation? Please take a moment. We could, yes. So which solutions did you come up with? Plus or minus 1. The other one is not giving us anything, right? Because when x squared plus 2 is equal to 0, you get a complex solution, which is not a real solution. It's not going to show on the graph, basically. So x squared plus 2 can never be equal to 0. Nothing coming out of there. The only thing you can worry about is x squared minus 1 being equal to 0. You could say x squared is 1, x is plus or minus 1. So those are the two intersection points. So this side should be negative 1. This side is positive 1. And now we're ready to integrate. So we're going to integrate the area function that we set up there from negative 1 to 1. Okay. And I ask you once again, yes, we could continue this integral from negative 1 to 1, but anytime I see symmetrical limits like this, I ask myself, can I make this 2 times the integral from 0 to 1? And without even looking at the graph, I can tell you that the answer is yes or no by looking at what is being integrated. Okay? If it's an even function, meaning that you have either all even powers of x, or in general, replacing x with negative x gives you the same function back. Is that the case in this situation? If you were to replace x with negative x, do you get the same function back? Yes. So that means you can actually go, in this case, also 2 times the integral from 0 to 1 of the above. And now we need to integrate it. By the way, in this case, the graph also makes it clear, right? Because if you look at the graph from the calculator, it was perfectly symmetrical, on 2 sides, around the y-axis, on this side and this side, these two areas are exactly the same. It's just the final answer with twice as much as any one of those two answers. Okay, all those integrals that we've learned in the last chapter, these are like so simple in comparison, right? How do you integrate 1 over 1 plus x squared? Arctangent, right? And there is no a. A is 1, so it's just going to be tan inverse of x. And minus 1/2. Integrating x squared is just as simple as x cubed over 3, going from 0 to 1. Okay, I need to know tangent inverse of 1. Does anybody remember? Pi over 4, right? Because at 45 degrees or pi over 4 radians, sine and cosine are equal. Their ratio is 1. So tangent inverse of 1 is pi over 4 minus, plugging 1 into the second part, we get 1 over 6. Now, what if we plug in a 0? Is anything coming out of that? What is tangent inverse of 0? 0, and the other part is 0 as well. So, and 0 times anything is 0. So this whole thing drops out. So really the answer is what we have up here. We could get common denominators. Let's get them at 12. So this top and bottom I'm going to multiply by 3. This top and bottom by 2. So I'm getting 3 pi minus 2 over 12. But now I can simplify the 2 on the outside with the 12 on the bottom over 6. So that's one way to leave our answers, 3 pi minus 2 over 6. Of course, you could also get a decimal approximation if you wanted to. So our first two examples have been the kind where you pick a vertical rectangle, right? And we use delta x or dx as our variable of integration. All the functions had to be put in terms of x. The limits of integration had to come from the x-axis as well. Now let's take a look at some examples that are a little bit different, especially some that will use a horizontal rectangle. Let's see. Okay, let's take a look at this one. Once again, find the area trapped between the given functions. Find area between the functions y equals x minus 2 and x equals y squared minus y minus 6. In general, what kind of a graph is x equals y squared? X equals y squared would be something that opens to the right, correct? And x equals negative y squared would be something, a parabola that opens, okay, the first one opens to the right, the second one opens to the left. So this one is positive y squared, the other one is negative y squared. Now in this case, we have something of the form a positive y squared, right? X equals positive y squared. So you can already see this parabola should open in which direction? It should open to the right, right, correct? Okay, and what will be the x-intercept? In other words, when y is 0, what would you get? We get negative 6. So this will be shifted basically to the left a little bit. you know, roughly speaking, it will cross somewhere around there, the x-axis. And I can also look at where it's going to cross the y-axis. So if I factor this, y minus 3 times y plus 2, for the y-intercept at x equal to 0, so where is it going to cross the rather the y-axis? At 3 and negative 2. So very roughly speaking, you know, we didn't necessarily find the vertex or anything like that, but we have a rough idea about what this graph is going to look like. It's going to be a parabola. And again, the vertex might be somewhere else. It may be a little bit up there or down there. But it doesn't really matter that much. All we are trying to see is which function is going to be on the left, which one is going to be on the right, and get a ballpark estimate about you know, the intersection point so we can check our work if there need be. Okay, how about y equals x minus 2? The y-intercept there is negative 2, right? So it's going to go through here. Y-intercept is negative 2. And how about the x-intercept? If y is 0, x is positive 2. So this is what the graph looks like for that one. And which region then should they be, are they asking about here? This region here, right? Trapped between the red curve and the black curve as we have drawn. Okay. What kind of a rectangle should we select as our representative rectangle here? One that goes up and down. Would that work? If you select one that goes up and down, over here the neighbors are going to be on the top and the bottom, the red curve, correct? As you move to the right, the neighbors are going to be, so if you pick a rectangle like this, but here the neighbors have changed, right? On the top it's the red curve, on the bottom it's the black curve. So it's not working very well. You cannot cover the entire region uniformly. Now you could do something else. You could split this into two regions, right? About this point right here, at about x equals 0. You could do the left side separately because these have the same top and bottom neighbors throughout the region. And you could do the right part separately. But why set up two integrals when you don't have to? You can go with a single integral if you pick what kind of a rectangle? A horizontal. So if we do that, what is the thickness of this rectangle? Delta y, right? So this is the kind of example where we're going to go right minus left. Everything has to be set in terms of y, and the limits must come from which axis? If you have a dy in your integral, if you have a delta y in your representative rectangle, it's always going to be the same thing, meaning your variable of integration must have a y in it, and the limits must come from which axis? From the y-axis, always. If you have a dy, that's the way it's going to work out. Okay, so let's set up our integral then for this question. Area equals, we'll worry about the limits in a minute. At the moment, right minus left. But remember, it would be helpful to first put your dy, because you know the delta y means you're going to have all the variables in terms of y in this integral. Remember that rule we saw earlier? It said f of y minus g of y. Okay, the function that is further to the right was given as y equals x minus 2. Could I put an x minus 2 here right now as my right function? What should I be putting? X is equal to y plus 2. You need to get that function in terms of y and then put it down. Minus, that's my right function, right? The straight line. The left function, that was already given in terms of y, so there we just copy that over. Y squared minus y minus 6. Okay, how about the limits of integration? What should I be doing for that? Right, we're going to get to that in a minute, but right now to find the limits, set the functions equal. So, like on one side, x equals to this, on the other side, x equals to that. So set those two quantities equal in terms of y. So here we have y plus 2 is equal to y squared minus y minus 6. Again, let me get everything on the right-hand side. That's y squared minus 2y minus 8. So two intersection points, we're getting 1 at 4, 1 at negative 2. Does that make sense, roughly speaking, based on our graph? It looks like, yes, exactly. They do intersect at negative 2 that we could see. And the other one does make sense on this graph. It looks like they're intersecting at positive 4. So the limits of integration will be from negative 2 to positive 4. Then let's just simplify the integrand. Could I do the double method here? 2 times 0 to something? No. The limits, first of all, are not perfectly symmetrical. What's inside that we're integrating is not all even power, so we couldn't do that trick. We got to do the whole thing as given. All right, so let me first simplify this over here. We've got y plus 2 minus y squared plus y plus 6. Okay, I'm going to write down the highest degree term first. Negative y squared. Then I have plus 2y. And then I have plus 8. Okay, before we go any further, let me see if there are any questions about what we have so far. Any questions at all? We graphed it, picked our representative rectangle, found our limits of integration, and now we need to integrate it, right? So let me give you a few moments to do this. I'm going to collect the fractions together first of all. And for the whole numbers, I got 16 plus 32. And distributed in negative sign, I have negative 4 plus 16. I have 32 plus 32, or 64, minus 4, that is 60. Minus 72 thirds, which is 24. Good. So we got 36.